Okay, so let's start. Can you hear me? You can hear me now, right? Yes, so. So, welcome everyone. Today, we move forward with the overview of computing infrastructures. Okay, so yesterday we have seen the general introduction. So, what is a computing infrastructure? 3 elements. First element, infrastructure. So this means hardware kind of things. However, hardware alone is nothing, right? We need a software that orchestrates a very large system, okay, and coordinate access to resources. And this thing is not only for, in general, a single application, but the goal is to support several services, right, that are offered maybe also to third parties. Okay. Here, something that we are familiar with is our PC. That is not. I mean, it's not for services. Usually, it's for us. But I mean, something we are familiar with in terms of capacity, in terms of memory that is available here. And then you see that we have several options. We have already covered the data centers that are the ones that are more representative at scale. Okay. And then we have also started talking about data centers and edge computing. Okay. So for what concerns data centers, we have seen that we'll enter on this next week. We have servers for computation. Today we have several accelerators to also to favor AI workloads that are really relevant and are still growing. We have server for storage, and we have server for communication. Okay, and so we have I mean, the characteristic of this system is also to be virtualized. So on the software side, virtualization is technology that allow us to build interesting services today, and is the software that really allow us to manage the system as a whole and to partition the resources across several applications. We then were focusing on pros and cons of data centers. We said here, these boxes are relevant for us not only to take a position for a priori a dogmatic position of what is good, what is bad, but is to understand and to focus for us to which are the relevant characteristics for making a choice. Because given an application, you are a computer scientist and you are in charge to decide what's the architecture of the underlying infrastructure to choose in a way that you can operate at best your application. Okay, so across the characteristics, we have seen that usually going to data center will lower costs because we can leverage on economies of scale, and as we see, these are implications also on the operating cost because of the cooling, because system at larger scale requires a lot of investment, are more complex. We have already seen that we are water-based cooling today. Okay, these allow us to achieve a better efficiency in terms of how much we can cool down a server room, but it's more expensive, of course. But there are economies of scale here too. Okay, so if you're current, for example, you consider the cost per watt that you have to sustain for cooling, then you will see that for more complex scenarios, you have more savings on the cooling. Okay. We have usually high performance because we can scale our application, and there are AI loads that scale horizontally. There are big data applications that scale horizontally. So, I mean, instead of running a big data query in 1,000 hours with the same budget, we can just run in 1 hour if we scale, if we launch the proper number of cores, for example, to support these applications. We have the illusion of to have infinite storage. We have the benefit also to have several versions of whatever we store in the data center, because usually one feature is we're able to access the history of a given data item. Okay, we have several rotation type, even for what concerns. So if you look at Amazon, you have a standard price, but there exists also Glacier, for example, where the data is stored on tape. Okay, and in that case, of course, to access the first byte, you take more time because there are robots that are taking tapes and plugging into the reader. Okay, but that's much more cheaper than the standard storage, for example. Okay, we'll dig into these too. We have higher reliability because of replication, and the nice things that are interrelated are universal document access and device independent, because I can access from my mobile phone the same data that I have on my laptop, for example. This is beneficial in the way we use ICT today solutions. Okay, these are the pros, and which are the limitations? The limitations are we said we require a continuous connectivity to get access to the services and the data. These usually introduce a latency, and these two problems are the ones that are the core for edge computing continuum. Okay, which is edge computing is the next infrastructure we talked about, and moreover, we have also some limitation in the hardware catalog that is not, if I want to buy an on-premise service, I can really make it custom according to my need for my application. Why sometimes it's not the case on cloud providers. We have issues for privacy and security, given the regulation. Okay, given the fact that if you have sensitive data, if you have patient data, you cannot just move to the cloud, to the data center. You need some more restriction. You need to follow up some rules that are set up from the government or from the European community, for example. And finally, here we really have huge power consumption. We've seen that there is an increasing trend in the last years. The energy consumption of data centers is about 4-6% of the electricity produced worldwide, which is a lot. And this also has an implication of in terms of environment footprint, because of the pollution that is generated by data center. And if we look at the trend of AI, we are happy because AI is growing. We are computer scientists, we are in the technology, okay? And there is an exponential growth of AI, and this exponential growth of AI implies an exponential growth also of the computing infrastructure, because we need more and more capacity. People are investing nearly billions of dollars for AI factories, AI data centers. Okay, this is a broad view of and recap of data centers. Hope you don't have a doubt on this. Please, if you want to raise discussion, curiosity, I'm not clear because I'm too fast, whatever, raise your hand and make a question. Okay, I love to have interactive classes. I don't come here to talk for 2 hours in a row. I would prefer to interact with you. Okay, and then we said, okay, let's move on because the data center are representative and will be the core focus of our course. But there is something else. The first thing I mentioned is edge computing system. The core idea of edge is twofold. The core issue really of cloud applications are related to the continuous connectivity through network and the latency that the network introduces. Okay, these are really the core problem of cloud. And if we observe the technology, we don't have only data centers, but something that is really growing fast is also the Internet of Things. Internet of Things means what? Sensors that are spread everywhere in devices, in your phone, you have many sensors. I mean, I don't know. You count how many steps you do. You count. You have some statistics if you run or fitness, whatever, right? That's one source. But there are sensors really everywhere in cars, into the devices that we have home, and this is really growing. As I told you, in 2022, we had more things that are connected. So Internet of Things means really that they are accessible through a network, through the internet even, okay, through internet technology in case, and they surpassed the things surpassed the human beings. 4.1 billion in 2022. We are about 8 billion in the world, humans in the world. And so the key point is, the key observation is also that we don't have only the Internet of Things with the sensors and actuators and data centers that we access remotely, but nowadays we have also some other computing capacity that is available. Okay, so we made the example of the drone that is taking pictures to process images of the wind farms, for example, and we made the example of smart glasses, next generation smart glasses with augmented reality features. Okay, the key thing when you decide where to put your application in the stack, in the computing continuum, in the edge fog computing, is the latency. Okay, we said if we need to take decisions, so actuation needs to be performed in microseconds, in milliseconds. Okay, you have to react fast. Then I should stay in the Internet of Things. Consider a self-driving car. I mean, there are cameras analyzing what's going on, okay, on the road, the pedestrians, other cars, and so on. And you cannot delegate the remote execution to for the decision to brake, to stop your car, for example. So in a self-driving car, even if this used to be the approach several years ago, nowadays on cars, we have a computation that, I mean, for the self-driving cars, we really have computation that is running within the car. Okay, so we stay here. Vice versa, if we can tolerate some second delays up to 100 milliseconds, we can perform some processing also in the intermediate layers, right, without reaching the cloud. While vice versa, if we can really tolerate seconds to minutes, we can perform and offload our computation to the cloud. Okay, so in the two examples that we have considered yesterday, for what concerns the drone scenario taking picture, so the IoT thing is the drone itself. It's running some components on board. It's taking decision if a picture is good or not, is blurred or not, is too dark or is too light or not. Okay. Then the processing to decide, for example, if there are no fault in your system are taken in the intermediate layer that for the drone scenario is the laptop of the pilot of the drone, right? And then whenever you decided that there are issues in your picture, to classify the fault in your system, then you interact with the remote cloud, okay? Because there you run more computer-hungry deep learning models that classify the defects on your wind farm, okay? So that's the cloud. That's what you run in the cloud. In the example of smart glass, the application usually is a single AI component, frequently is a simple AI component, which is a deep network that you can cut in different positions, okay? So you always run the full, the single deep neural network, right? But then what you do is you split this computation, and the IoT part is what? Is the glass, is the frame, okay? Where you have acquisition from camera, you have some initial processing. Then the intermediate layer is your phone, okay? And the remote layer is still the cloud. Okay, here the challenge is you have two networks in between. Glass to phone, Wi-Fi, phone to cloud, 5G, and there is a variability in the network, and there you have to process in few milliseconds. Okay, there are applications that really you have a time constraint that the frame rate should be very fast. You can process one frame in 40 milliseconds. Okay, so you understand that you cannot do this on cloud. You do so only if the connectivity is very good and you want to save energy. Because if you offload the computation, you extend the battery life of the local devices. There is this trade-off between performance and energy consumption. Okay, so that's the broad overview of the thing. So we are driven by latency in our choice mainly. That's a challenge because really whatever we see in the course related to data center and cloud computing is a current technology. Computing continuum is still, cutting edge technology and a research environment. European communities, for example, is investing a lot of money for research on computing continuum. And that challenge are related by the fact that you have heterogeneous devices. So in the two different examples, you have always a cloud, but the edge layer was a laptop in one case, was a phone in another case. The IoT thing is a frame in one case, and is a drone in another case. So you have a heterogeneous technology, and to manage this heterogeneous technology is difficult in general. Okay, and you have also to, these offloading decisions that you take at runtime are also challenging because you have to fulfill performance and minimize energy consumption use. Okay, so this is challenging. There are no, standard solutions for this. Most is still ad hoc per application. Okay, the technology, the solution you plug to exploit at best hardware and software and make your application and user happy. Okay, that's the general scenario. For what concerns the technology here, you have some example of servers that are usually the one that you put at the intermediate layer of the computing continuum. Okay. Here you have nowadays really in this server are modern servers that include also some accelerator on board. Of course, probably you don't probably run the most advanced GPUs. You don't run the most power-hungry GPUs in an intermediate layer. Okay, but it depends where this is located. Okay, so you have a scenario of solution. These are more or less medium-sized servers. Okay, what you have here, and you still have if we continue the comparison with the data center and the other computing infrastructures, what you have is still high computational capacity. Of course, you have in a data center, you have 10,000 servers today. Here, if you have a small data center that is reachable through a 5G network, 5G antenna sometimes, then you have a limited number of servers there. You don't have the same capacity as a data center scale, but you have a small, medium-sized data centers in that case. The computation is more distributed because there are solutions where you don't really plug this device on data centers, but you put on premises. For example, in the realm of self-driving cars, in the research path, some researcher had the idea, for example, to plug some servers located near to the junctions, because near to the junctions is where you have more pedestrians, so you have a heavy load computation that maybe on the car itself you cannot perform. So you can offload some computation on these servers plugged in the intersection of our roads. Okay, this is still ongoing research, as you expect. Here you have a better privacy and security because you are sometimes these servers are located on premise, in infrastructure you own. Okay, it's not something that is a remote cloud provider, and you have usually reduced latency because, for example, consider airport. The application is still a video processing application where you are trying to identify what's going on in an airport. So, for example, if someone is hitting someone else, you raise an alarm, or you are looking for some specific bad guys, okay, that you want to identify. You know, they are at the airport, they probably can go to the airport, you want to identify them, right? So you have some processing that happens even within the cameras. Today, in the modern cameras, you can run some little AI tasks, okay? But some heavy processing can be done in servers that are at the airport, okay? So here you have better privacy because you are not sending the videos to the cloud, but you are processing on premises, okay? So you have a better privacy and lower latency. I mean, the servers are on premise, are not remote, so you don't go to a very far, network to verify location, but you process in the local area network, which is fast. Which are the issues? The issues are related because of the power connection. These are servers. You cannot run on battery. Moreover, you still, for some processing, require some cloud connectivity. If you look at the processing, maybe the processing with the cloud is intermittent, is not continuous. You offload a heavy task, whatever you cannot run local, okay? But you still require in this system usually connectivity to the cloud. Then the other box that we can analyze in our XY axis are the so-called embedded PCs. Here, I mean, the cost related to the previous server were about, I don't know, 5K, 10K per server. Here, we are talking about devices that cost a few €100. I mean, a Raspberry Pi. Who plays with the Raspberry Pi, though? Raise your hand. Good. At least few. Thanks God. There are a few guys playing with Raspberry Pis. They are really cheap, right? $100, 130. I checked yesterday on Amazon. Is about 140. These are mini PC. Okay. The Jackson Ori is one of the cheap NVIDIA GPUs. They are a bit limited. They're not the high-end thing, but it still cost, I think, €200-300 each. And then here you have, I mean, these are also Orin, and the Google Coral are for AI tasks too. So you have some AI acceleration on these devices too. And these, for example, these are ARM-based frequently. And sometimes these boards are similar to whatever is the logic that you run on your phone. There are some that are really based on the same. If you look at the one that are based on the Snapdragon, for example, are exactly the board, I mean, the infrastructure that runs in your phone. Okay. So here, which are the characteristics? Here we can go more pervasive. I mean, given the task, you can plug one of these into the devices that you have home, for example, or maybe this something inspired to this hardware runs within the smart cameras that I told you. Okay. So it's more pervasive, are more widespread. They are not located in a data center. You can plug where you need. Another area of research is, for example, the edge. It extends to satellites. Okay. So, for example, on satellites, you perform some processing. You do some compression, please. Then, of course, you have some processing on data centers that are on Earth. Then, right? So, in that case, the IoT world is the satellite. And on satellites, for example, you plug a Raspberry Pi, kind of a hardware. And there, I mean, in these cases, you still have issues with the power consumption, because on satellite, I mean, you have solar power, you have batteries, you run and you recharge your batteries whenever you are in front of the sun. Okay, so also here orchestrating the computation and trading off the performance in the computation with the availability of energy is still important. Okay, here we have still solution to develop our application like in our PC. These are mini PC actually. Okay, Raspberry Pi is a small Linux server. You can see it is a small Linux server. And it's not, I mean, really, there are development kit, and there are usually active communities. So developing application on this kind of environment is not that bad. It's not that difficult. Okay. Which are the issues? We have a still high power consumption. We can sometimes run on battery, but we have some limitation. And moreover, we have to perform some hardware design for what concern the sensor actuator usually, right? Because that's a mini PC, and you can imagine if you have to control a camera, then you need to to plug the camera to have the control, the driver to access the camera, and so on. Okay, so there are something more. You still need to integrate the actuator and sensors and to perform the integration. Okay, these are the key characteristics of this kind of thing. Finally, the last one are really these kind of devices, these example of devices that I put here. As you see here, what we do is, while this guy still runs at a gigahertz level, okay, it's not like your laptop boosting up to 4 gigahertz, but we are from 1 to 2 something gigahertz, okay. If we go to the other class, which are the microcontrollers that we have in the Internet of Things, if you see here, we have a few megahertz in terms of clock speed, okay, and we have severe limitation in terms of memory. All the devices here are less than 1 megabyte for the RAM, and about a few megabytes for the flash memory, which is your storage. On the flash, usually you store your application, okay? And that is the storage facility of your device. If you have to save some permanent data, you can save on device on the flash memory, but you have a severe limitation here. Here we are even below kilobytes, okay? So which are the characteristics here? They can really be ugly pervasive. Okay, you can, next generation pacemaker will be based on this, for example. You have a different technology also for the wireless connectivity. You don't even run Wi-Fi in these things. You have a Bluetooth Low Energy, Zigbee. You have these protocols that works also discover the network as a facility, as a feature, and have low power consumption. Okay, they all run on battery power. Okay, and they also have low cost. Here, really, we're talking about few dollars. Each of these devices, few dollars. For example, if you have an espresso machine home, you have one device like this one inside that go over and automate the thing. And then, I mean, you have sometimes integrated also the sensing, the actuator part. Okay. What are the limitations, the characteristics? We have low computing ability, clock at a few megahertz, constraint on energy, still because we run on battery, constraint on memory in terms of storage and RAM, and here programming is much more difficult because you don't, here you still have, in the previous slide, you still have operating system here. Okay, you can rely on operating system for running your application. Here you don't. Okay, so if you have to, I mean, you have to write the software to integrate the sensor to access the sensors, for example. Okay, here you have usually development kit that are custom by the provider, the hardware provider. Okay, and so programming is much more difficult. You usually here you are low level, C, C++, assembler sometimes also. Okay, and So development is not easy, and of course these are proprietary usually, right? So if you go to STM microelectronics, you have their own development toolkit. If you move to another vendor, you have another development toolkit with a different way to develop application. Okay, so it's more difficult, and of course the portability of the application is much more difficult, because whenever you develop something for one device, it's not easy to move that software to another device. Okay, these are the constraints you have here. So as a wrap up, we have usually in a computing infrastructure 3 layers. One is the hardware layer. So it's the physical resource that on top of which we can run up our application. Then on top, the highest level, we have the application that is the reason why we are developing our system. Okay. And then there is the software infrastructure in between that is a software that allows us to develop, deploy, and run our application usually efficiently. Because in the most advanced system, you have a trade-off between performance, energy consumption, latency, and so on. Okay. So in our course, we will cover mainly hardware and software for what concern, environmental software, not the final application level thing. And in particular, for hardware part, we will focus on the data center. And the software layer will take a look to the cloud technology, virtualization technology. And as an example of software, we will consider a cloud-based machine learning service, okay, solution. Because again, it's growing fast, so it's good to devote the last class to machine learning as a service. Okay. Any question on this? Is it clear? According to the question I received yesterday, you were a bit confused of for the edge computing part of what is running the intermediate layer, what is running the IoT layer, and so on. Hope that wrapping up simplifies a bit and the concepts are more clear now. Any question? No question. So you said AWS opened a data center in Milan, and edge computing is something that you can access quickly. Actually, the AWS data center is not in Milan, but is in Piacenza. Okay, and if you reach something to a wide area network or a 5G network, it's something which is remote. Okay, so that's the cloud. AWS data center, they are starting, we mentioned today, we move to another topic, but there are also cloud providers are setting up some local location, okay, local edge location where you can run computation close to where you collect the data, okay. So for example, let me, from my experience, let me mention another example. We did an application for which is based on AI, is for farming 4.0. The core problem is, you have in vineyards, the problem you have is you have to spray the chemicals anytime your plants get a disease, your grape get disease, okay? So in that case, the edge, the IoT, let me say, was a camera. You were collecting what? The sensing part was the camera that you mount in front of your tractor. An harvester is a huge machine. We're talking about machines that cost 150K, okay, euros. You have cameras you have a Jetson board, Linux PC based on Jetson 2, and you have some local processing there. All the process, and what is your actuator there? The sprayer, because while you move in front of the plants, you have to spray if there is a disease on the plant. Okay, so in that case, all the computation is performed on the tractor, in the harvester. Then, where you have your server at the farm. Okay, when you go back, you download the videos, you gather statistics because I mean you have also GPS running on the tractor, so you know where you sprayed, in a way that you can build automatically a map of the disease of your field, for example. Okay, and that's what's going on the intermediate layer, which is on-premises server. Okay, and then the computation, the interaction with the cloud was what? Whenever you are in the farm, okay, your server can upload the videos taken, okay, and on the cloud, our colleagues were running what? Some machine learning model that were able to predict, for example, how much grape you were producing, the yield. You wanted to predict the yield, okay? This is what happened in the cloud. So if you have a remote connection that introduces latency, whatever you shout is the cloud. The intermediate thing is something that you can, has limited capacity usually, because an on-premise data center is, I mean, it's not 1,000 nodes, 10,000 nodes, but I don't know, you have 100, let's say. And you can access quickly through a local area network, okay? And usually the Internet of Things is where you get the input for your application. Sensing means getting input. Sometimes you have actuation because you want to control the system, okay? So you have sensing actuation which are on the Internet of Things because it's where things, real things happen, okay? That's, hope that is clarified, okay? But however, for example, whatever you're mentioning in, as I said, AWS, for example, is providing some edge location facility, okay? But they usually run their servers within the telco provider, okay? So telcos are good to manage antennas, okay? Cloud providers are good to manage virtual machine and run computation, okay? They have agreement in a way that they run the virtual machine within a data center that is owned by the telco provider, but is managed by the cloud provider, okay? Because you have different skills. Really the edge computing is an opportunity for the telcos, because there are new services that you have to really run close to the to where you gather data, and you gather data through network, through 5G network today, okay? So that's the intermediate layer is really plugged into the telco, okay? Okay, any other point, curiosity? Thanks for questions, okay? At least I go out of my path, and okay. So let's move on. Then, if you don't have additional questions, it's already 1:10. Let's move on in the overview of data centers. In particular, let's take a look to the architecture and the rack structure, okay? And let's see how application and data center infrastructure have evolved in the last 20 years, okay? So what happened? If you look at the way we developed application in the last few decades, what happened is that we moved from monolithic application, okay, that used to run on a personal computer, okay? If you have, I don't know, an application for managing your career in Politecnico, imagine that 20 years ago, you used to have a desktop-based application, all monolithic, okay? They were running on fat client architecture, a PC with storage, memory, and significant computing capacity. what happened recently is if you come from, I think you have, you already did the information system with who attended Professor Capiello classes? Anybody? Capiello, Plebani? No, Scarnapieco, right? She's the other one. Okay, yeah, this area. You managed, I think, I even wrote the book at that time, collaborating with them. You know that a monolithic application today is split into UI, user interface, application logic, database. Okay, and what happened today is really new applications that are web-based mainly. So you have data and application part that run on servers, usually on specialized servers because the VMS needs fast storage. Application server usually is more CPU bounded, so you need a fast CPU, more memory on the application server layer. And finally, you have the UI, and the UI is the only thing that run on the device. Okay, and so most of the computation now doesn't run on the PC alone. Okay, it's not. I don't have a monolithic application that run on a single PC. But really, I have this application logic that is split, and so I run usually the UI on even mobile devices, okay, on thin client, and the application logic and the data are stored in data centers, remote data centers, or nowadays even to cloud computing. Okay, that's the evolution. Okay, from monolithic to three-layered, at least, applications where the UI run on mobile, on thin clients, okay, and the application logic and the data are executed remotely in a data center. Why this happened? Because this is a win-win for everybody. Everybody means the end user, the software provider, and also the infrastructure provider. So from the end user, you have a easier management of your application. You just connect from your mobile. You don't have to do backup. You don't have to perform updates because if there is a new release of the application, you download from your browser, right? So you really reduce the management cost for your application. The scenario of 2000s where I have a single monolithic application, you have to backup your PC, right? So in a company where you have 100 PCs, you have to go around, backup 100 PCs, okay? Vice versa, now you don't care about the PC because the PC is just, so you need a browser running in the PC, right, to access the application. And the data is in another place, you don't need to backup, so you really reduce the management effort. And moreover, as we said yesterday, we have also ubiquity access because I have to, I don't do so. But for example, if I have to check the status of your grades, I can do so from my office, from home, or anytime I come in the subway, I can double check something, right? So I can work even when I am in mobility. So that's the win-win for the end user. The user is happy. You usually reduce the cost of your application. Backup management, and you have ubiquitous access. While on the other side, for the software vendor, you always, I mean, if you really stick with the software as a service, we cover this during the course. We usually have some advanced library that you can exploit to develop your application. So you really are faster the software development activity. Moreover, what is really relevant for you, I mean, if you build up a software application for what concerns the server side, you don't have heterogeneous hardware. You go to cloud, you say, okay, I decide to host in this given application server my code. I decide to run on this specific DBMS my application. That's something which is not heterogeneous because you choose the configuration. You always stick the same configuration for your application. The only worry is the client side, right? Because there you have different terminals probably, right? You have different PC, different browsers today. Even if you have your application web-based, the headache to manage heterogeneous configuration is only on the client side. But they are, I mean, more or less, you have to take care if you are developing for, I don't know, for Safari, for Chrome, or, I mean, but they are also using these issues on the standardization of the browser technology to ease the development activity for the developer. So the key point here is you really have to deploy your application on a set of hardware that you decide you keep homogeneous, because in this way it's easier to maintain your system. Okay, so also the software vendor is happy because he can develop faster the application. He also can reduce the management activities related to software because you have a homogeneous environment of your choice. Okay. Finally, you make also happy and the life easier for the hardware provider, because that's really the guy who owns and manages the hardware. And usually, I mean, in same place, you can update the hardware itself. You can read you say, okay, look, I have to plug some AI components in my application. I need some accelerator. You plug and install homogeneous hardware also here in a single place. Okay. And also here you achieve economies of scale, as we said, because you buy 100 GPUs, not only one, so you have better discount by the provider of the GPUs, of the provider of hardware. Okay, so you understand that this scenario that we are so moving towards data centers enabled computing has benefit both for end user, software provider, and hardware vendors. Then, if you look really the evolution of applications, what happened is also in the last 20 years, we developed a new application that really cannot even run on a single device, on a single PC, but really need the scale of the data center. Okay, two extreme examples: search engines, for example. You know, I mean, search engines nowadays, how it works. We have to gather all the web pages that are available on the internet, right? Store the pages in one place, perform some processing of each page, because there you have the keyword. You look for the keywords that you refer in the search. Then you need some ranking algorithm. The way that if I type in my keywords, I just get the most relevant pages. And finally, in a search, you have to be very fast, right? I mean, if you type in a search in the search engine of your choice, you get answer in a few milliseconds, okay? And usually a single query runs on 100 CPUs. It's not a single server that is computing the answer of your search, but the single search is supported by several nodes that run together and provide the answer of your search. Okay, so that's an example of a service that cannot run in a single node, but requires several nodes within a data center. And another thing that is, I mean, today is in the news almost every day is, of course, AI. Okay, if we look at AI, machine learning, deep learning loads, now we are. What is hot today is the generative AI thing, right? This started about, this is a news 4 years ago, the link here, where The Guardian published an article on AI that was written by AI itself, okay? And so this was groundbreaking, okay? Because from this, we really have a lot of new applications that are still evolving today. So you have the Copilot kind of things, you have the code generator, but you have also fancy, I mean, you have a ChatGPT that today is even used for search. That's scary because this technology still have some hallucination, even if they are trying to mimic this kind of thing. Then you can do really fancy application like, you know, you can have a bot that behaves like Einstein and you can answer questions to Einstein, for example. There are this kind of fancy thing too. But for sure, what happened, and this, I mean, will be the motivation for the accelerator part. If you look at these models, these are an example for the natural language processing models. There is a steady growth in the number of parameters, how large these models are built, okay, that is really growing fast, and the computing capacity that we are installing in all data centers worldwide cannot even cope with the growth rate of the models themselves. Okay, so that's the fix of ChatGPT thing. That's the data of ChatGPT 3. ChatGPT 3 would run, I mean, in a single, I mean, this was trained, I think, for several weeks on 2,000 GPUs at the time. If you run on a single, you try to train this kind of models on a single node, it will take years. This data is related to the high end. The V100 used to be 4 years ago the equivalent of A100 today, the one high level GPUs. Then that's the cost. Really, this costs millions. I mean, to train just a model. Okay. Are you following the DeepSeek stuff today? Anybody? You know, there is a Chinese company. They say, "Oh, look, I'm doing something that is as accurate as GPT-4, but while GPT-4 was the training costed several billions, they said, oh no, I did my training with a 5.6 million only. But it's not really clear. They are for sure efficient because it's based on the ones who knows the thing, on mixture of experts. So anytime you interact with a model, you are not using all the network that consume a lot of computation, but you are branching, you are just working with a subset of the network, and this requires lower computation, lower power, and lower memory too, okay? But however, I mean, it's not clear because it looks like that they did some distillation interacting with the OpenAI API, okay? That's so they learn a more efficient model starting from OpenAI models that really cost a lot, okay? And if you look at the facility, they say, okay, I spent 5.6 million, but only for a single training. And behind the single training, you did several more. And they also have, I mean, the company is a profit company, the DeepSeek one. But behind, they have a very large infrastructure with 1,000 GPUs, 1,000 nodes around China and the world, okay? So it's not clear what's going on there. But if you look at the proprietary model, that's the trend. They are really growing. These are some data because, as I told you yesterday, for a single prompt, from up, let's say, between 10 and 50 prompts, you consume half a liter of water for the cooling system. So also the inference has an important impact on the environment. And these are the data related to the training of GPT-3, which is previous generation, okay? And actually, you consume, you generate a carbon dioxide emission. There's a new car in Europe. They say this because the cars in US, I mean, they consume crazy. I mean, the cost of oil is much lower there. They don't care how much they consume. I mean, they have a very large car, big car, and so on, right? They are not efficient from the oil perspective, the carbon dioxide emission perspective. So a European car is considered something green for them, and that's the much. I mean, it's the same as the full life cycles of 5 cars in Europe, building up the car up to you dismiss the car. Okay, just one training of ChatGPT 3. Okay, and the trend is still this because it looks like, I mean, these are some guess because they never I think, the best of my knowledge, they never said how large is a GPT-4, GPT-4 model behind. But here we move from 175 billion of parameters, which is a GPT-3, in 4 years, to 1.76 trillion, so 10 times larger models in just 4 years. Okay. So Altman really said that he spent 100 million for training GPT-4, and he's also trying to convince the government. These are some results on the accuracy you achieve. It's also multimodal because before you can generate text, you can manage text with GPT-3. With a new model, you can also generate images. For example, you can ask processing images. You upload documents including text and images, and you can really query both on text and images, for example. These are some data related to accuracy. But recently, this is something that he did last September. It was getting in touch with the US government asking for gigawatt-hour power data centers. I mean, as I told you today, we are about a megawatt, 10 megawatt, 100 megawatt is the size of a data center. Gigawatt you achieve plugging directly to an atomic power plant. Okay, that's what we are talking about. Gigawatt data centers is the capacity, the power consumption of all data centers located in Virginia. And usually in Virginia you have some cheap virtual machines because they are based on brown energy. Okay, they're not green energy. Green energy, unfortunately, it's expensive. Okay, is intermittent, add more complexity in the infrastructure if you want to use solar or wind power data centers. So that's what we are talking about. It's not, I mean, there is now still in place one single gigawatt data centers, but that's probably the trend. I mean, also in US, I think the Stargate project is the investment is about 500 billion on AI infrastructure to favor the advancement in Gen AI. Okay, this kind of technology. So that's the general trend. And of course, you cannot run this thing in a single node. Training these kind of models takes weeks. You are really ingesting. You know, sometimes they are in the news because they are violating copyrights. They are feeding in a training set, whatever you find in the news, the books, violating copyrights sometimes. That's all. I mean, there are disputes for OpenAI, Meta, NVIDIA themselves. I mean, they are really feeding this model with all the knowledge we have, all the text written in the world. Okay, you cannot process this thing on a single node, on a single PC. The training happens exploiting 1,000 GPUs that are used at the same time. Okay, that's the general trend. Then, if we look to something that is closer to us, I mean, that's here. There is also a video, a nice video. I suggest you to take a look. This Gen AI really happens today. The development activities, right? So, even who is using Colab? Colab guys, don't be shy. I want to have some statistics. Please raise your hand. A few? Okay. Too few. So yeah, you have seen that with Colab, for example, you have Gemini that is integrated. So you can ask, you can really type, and you can type, oh, please provide a Python function that given this input is doing this, and that. Okay. Sometimes you have some bugs, and then you can ask for a solution. Okay, provide some suggestion for the solution. Okay, so here Spark. Who is familiar with Spark? Nobody? Few? Okay, that few. Spark is, as I told you yesterday, and we will go back to this probably to this today too. Spark is the reference engine for big data today. It's in a memory framework that is used to really perform some parallel processing for big data analysis and big data machine learning too. And actually, they have also integrated with Spark. GitLab code was part of the training of ChatGPT-4, and you can also ask querying for please give me the code for doing this analysis. But for example, you can also ask, you provide a schema, and Spark understands the schema, so you can really write even in a natural language the query. So you say, okay, I would like to have a report with the selling product in last quarter grouped by region, for example. So you just type in this in natural language, and the AI behind, the generative AI behind, understand the schema of data, understand your request, and automatically generate the Spark code that you need for getting your plots, your analysis. Okay, so computer science is a specific case for for Gen AI applications, and is where we have good results today. This Copilot thing works. I also teach programming course. It's not easy to me to manage this stuff because if you try to program just relying on Gen AI, you don't learn to program. Forget. Okay, but it's like to have an advanced tutor, especially anytime you have a bug, you have a help. My suggestion is always to try to dig into the problem yourself, because this is the way you learn. You understand the problems, but after 3, 4 tentatives, then you can ask an expert that could be your professor. It's easier to have Gemani close to you than your professor close to you, probably, right? So, but try yourself first, because you are also computer scientists, so you should be the good one in coding. Okay, this is a video of what's available on Spark. And so if we look at the evolution, we started with small data centers. Okay, we'll see the characteristics of small data centers. And if we look at the last decade, what happened is we moved from data center to warehouse scale computers, warehouse scale data center. What does it mean? We are talking about very large data centers, okay, where we have really several nodes that run here, okay, and you have a single, still the definition of the computing infrastructure, you have a single software that allow you to orchestrate the access to the resources in a single coherent technology to manage the underlying infrastructure. And so usually, if we look at really the evolution, so if we look at what Google was doing in the early 2000s, they really built a single internet service, which was the search. Okay, and if we look at the characteristic of these warehouse scale computers, the application they were running were really limited. They were running 5, 10 programs like the search engine, the crawler, the ranking algorithm, right? They were not running anything. They were really running a limited set of services, okay, that usually were interacting each other. Okay, you have a few services that were interacting each other to build services like what? Search engine, email, maps, machine learning. Two examples of something that was developed for warehouse scale computing. Okay. So this is the way this data center look like. Okay. So all these nodes were co-located in a single very large data center. Why? Because I need computing, I need storage, I need networking, I need to protect the running facility in a single location. In the data center, you don't just enter like in university. I mean, there are controls like in airports, for example. I cannot access, I told you, we do have a data center in our department, but with my badge, I cannot enter my data center. I have to go with the administrator to enter, okay? Be aware that we have a small server room that is, I think, 40 square meters where we plug all stuff. And be aware that just the server room empty, just the cooling, non-redundant cooling 10 years ago costed €500,000 of euros. Okay, so the empty server room, because you have racks, you pay the cooling, but then, for example, you have also issues for in case of fire, so on. Okay, so there is a cost in the building too, as we will see. Okay, and vice versa. If we look at a traditional data center, is the same as a warehouse scale data center. They are not, because they usually have a very large number of very small size applications. So I don't know, you have the software for managing the administrative part of a company, these kind of things, the one with which you use for computing salaries, the one for tracing order to providers, tracing the transactions with your customers, this kind of thing. They are all heterogeneous, they are small size, okay? And usually in this data center, in this small size data center, usually you have one application, one server, okay? The reason why is because if you have if you collocate two applications on the same server, if one application fails, also the second application fails as issue, right? You have if one application is doing memory leakage, early or late you are saturating the memory of the physical machine, and also the second application crashes, right? This is what happened. So to avoid these, you have one application, one server, which you understand that's very cost inefficient, because as I told you, the average utilization is just 10%, 15% for a single application, single server scenario. In this case, you have many servers, you are paying a lot in terms of room for your data center, your building, you are paying a lot also for cooling and for electricity, okay? And usually, while in the warehouse scale, you have these few services that really interact with each other to develop the final functionalities for the end user, vice versa, here you have kind of monolithic applications that they don't talk to each other because they solve a single task, right? They are not really tightly integrated, okay? And usually you have also in a single data center, sometimes you really have that's a kind of a co-location scenario where you have a single data center that is used for managing the resources of different companies. You don't even have a single organization, but you're, as a provider, what you do is hosting application for third parties. Okay, these are the characteristics of the small data centers scenario. Okay, so if you really look at the single traditional data center, look like this. I have a single company. I have my own IT infrastructure, and I have just my own users. In a co-location scenario, what you have is you really have separate servers that are managed for different companies of different end users. Okay, so that's the scenario of a traditional data center. Okay, good. Questions? Issues? Good. While vice versa, we said that usually the warehouse scale data center are owned by a single guy. Okay, these are the most important names. Okay, that run vice versa to make their life easy. They run homogeneous hardware, while vice versa data center usually it is a co-location thing. You have also heterogeneous machines. Okay, And so the key characteristics of this warehouse scale data center to ease the management and the maintenance of your system, you have homogeneous hardware, which is controlled by a single software layer, and you run a single application on top. So they are very different, okay? And nowadays, so here you really have the scenario, right? You have homogeneous hardware, your own data center, you are the single owner, you serve several customers spread around the world accessing your internet scale data center like ChatGPT, like Google Search. Okay, that's the scenario. Okay, but nowadays what happened? Nowadays what happened is the following, right? We have a traditional data center and right, and warehouse scale data centers that are also becoming cloud providers. Okay, and in the cloud you also run the application that are I mean, they are not warehouse scale. The single application interact few, right, and they are heterogeneous between each other. Okay, what is the enabling technology? That's the key thing. Okay, nowadays we run the software that we used to run in traditional data centers in warehouse scale data centers, and the reason and the technology that enables this thing is virtualization. Okay, this virtualization. What's the path? The key point is so in a single facility, a warehouse scale data center, in a cloud data center, we can still run the internet-based service, okay, but we can co-locate within virtual machines traditional software, traditional systems. Okay, so why, in your opinion? A few minutes. Very good point. If you look at Amazon, okay, I don't know if I told you yesterday, they earn, let's say even in all data, on average during the year, their transactions are $5,000 per second. Okay, that's the average over the year. But of course, during the Black Friday, you have a peak, right? So that's the same scenario for them. They say, look, I have a very huge internet infrastructure. The reason why is, I told you yesterday, right? 100 milliseconds more, 1% lower income cause lower accesses, right? For 100 milliseconds. And here also that's a data that I didn't tell you yesterday. To improve by 100 milliseconds current technology, you need to invest 10% more in hardware. So there is a trade-off, what you earn and what you pay for providing good performance. Okay. And the key point is the same for them, right? At the peak, I need I don't know, the 100 million data nodes that I have worldwide, but during the year, the average utilization is 10-15%. Okay, so they started renting really their own hardware because otherwise they were oversized if we consider a mean load. Okay, so what they did was they were saying, look, I have more capacity that I can rent, really I can earn, and I can get more money from renting my hardware. Okay, so from their point of view, okay, that's the key thing. They run. See, the internet service for Amazon is what? The e-commerce side. And what is the new thing they offer? It's still a single application. They sell virtual machines. Okay, so the virtualization is the second application they offer, right? And that's the way we move that. So what is cloud computing? Cloud computing is exactly based on virtualization technology, okay, that changes the business model, because the virtualization in 2005, let's say, was used at enterprise level just to consolidate hardware, because as I told you, one application, one server, 15% high energy consumption, okay? Thanks to virtualization, I can collocate my application in a single server, okay? So you can really replace hardware. I mean, if you have 4 nodes, you can just keep one, right? And you consume a single server power consumption, not 4 servers power consumption, okay? That's thanks to virtualization. That's server consolidation, right? That's early 2000s. But then cloud computing, what does it mean? I offer the virtualization services to third parties, okay? And the new scheme is a pay-per-use scheme, because in the cloud, we pay just for the CPU and memory that we use per time unit, okay? And so that's the evolutionary path. But from the provider perspective, what you sell is just a virtualization service, okay? Which is good for them, because they don't want to mess up with the internal applications, right? They give you the virtual machine that is as a reference image with a given operating system version that maybe is patched, is updated by them, right? But they don't enter in the mess up of the software that you run within the virtual machines, okay? And that's exactly the picture that we have today. We have the traditional internet service. That's the reason why the internet service provider started his own business, right? And then whenever you have room and capacity, you rent the capacity to third party, okay? That's the evolutionary path that has been achieved, okay? Okay, so if we really look at this system, in this system, really we should see this warehouse scale computer as a single system itself, okay? The node, really the software allow you to see the full data center as a single machine, okay? With the same software, you really manage multiple nodes as this is a single system, okay? So if we go back, that's also the same path that has been taken with MapReduce and Spark approach, right? In Spark or MapReduce, let's go back to the example we raised yesterday on computing the average age of European citizens, okay? So as we said, I cannot store this thing in a single node, this data, because the local disks are not enough to store petabytes of data. So I have to spread the data across the different servers. Then I have a software layer. How I perform the computation? I write a simple code, okay, which is the same if I'm using a single node or if I'm using other nodes, okay. Then this code is shipped to the servers where the data runs, the data is stored, okay. Then what you do here, you perform the average computation according to the local data, okay, according to the citizens that you store locally, and then you perform a single aggregation where you compute the total aggregate of the mean given the partial means, okay, that you computed, okay. So from a Spark point of view, from MapReduce point of view, that's really a single system, okay? And that's the same for what concerns the virtualization orchestration software, okay? Because you can really manage and deploy from a dashboard your virtual machines on the physical hosts, okay? And moreover, we have, as I told you yesterday, we have also some advanced solution that if one node fails, you transparently migrate the applications without using computation even today. Okay? If you, if the load becomes lighter, then you can migrate. So now I'm running on 1,000 nodes. Then I have to run in 800 nodes. What you do is you live migrate the virtual machine running on the nodes that then you are going to switch off, for example. Okay, and so way you save power, you save energy for the cooling, and you reduce cost at the end. Okay, so that's the thing. Okay. So the key point is how many. What's the approach of a cloud of this warehouse scale provider? Do we have a single huge data center, or we have several data centers spread worldwide? The answer is the latter, right? The scenario is the latter. Usually, we have several data centers that are spread around the world. Okay. And the reason why is you reduce latency because, again, go back to Amazon. If I have to buy my stuff in US, I have to access their site through the way data connection. I have a high latency, okay? So that's not good. So they have located in this data center worldwide, also close. You see here, they are close. This is both Microsoft and Azure a few years ago, close to big cities, large cities. The reason why is that here I have a lot of customers, okay? And then, so in this way, you can really reduce the latency and you can improve the throughput of your applications. Okay, the latency if you are close. We are not as close as in the edge, okay, of course, in the edge computing continuum, but I mean, it's faster to access a data center in Europe, from Europe, than accessing the data center in US, right, from Europe, right? And so in this way, what you do also, you have what do you think? We said that virtual machine, we pay by seconds today. But what do you think? The price of virtual machines is the same worldwide or not? If I access one machine, 4 core, 16 gigs, and I pay $1 per hour in Europe, is this the same in US? Is the same in Ireland? Or is the same in China? What do you think? One at a time. What do you think? What is different? What is cheaper? Maybe. Ireland is cheaper, for example, because of the tax rate. I mean, there are issues also on the tax payment of, you know, also Trump is saying, oh, you are treating bad our US companies, you have $1 million of fees because they are violating the rules you have in Europe and so on, right? These kind of things you read in the news, right? So the key point is the cost of ATM depends on what? On the hardware, for sure, but depends on the cost of the energy and the cost of labor, right? The tax rate and so on, right? So as I told you, in Virginia, they have a lot of data centers because they are carbon-based. The electricity is mostly carbon-based. It's cheaper, right? Vice versa, the data centers located in California, they have some, they consider some environment, the governors, thank God there are also the governors that would like to take into account the climate change. And if you consider California, I mean, it was scaring, all Los Angeles was burning for days, right, recently, right? So they take care of these environmental issues, but of course they use more green energy, and the green energy there is more expensive. In general, also the labor cost is more expensive in California than Virginia. So, I mean, you have different costs, okay, across the worldwide. Then what you do, you try to co-locate your applications close to the users, right? So if you have an e-commerce site, that's exactly what Amazon does. If you have an e-commerce site, you would like to have a location in Asia, a location in Europe, a location in US, because we have different time zones also, right? So now is 2 p.m., almost 2 p.m., is 8 a.m. in New York, and is 8 p.m. in China, for example. So our activities, usually you have, if you look at the peak, that's all dirty. If you look at user activities, that's the time of the day, okay? These are the number of active users, let's say, the y-axis, okay? Usually you have a kind of bimodal distribution like this, okay? Right? So the peaks usually are located between 8 and 10 and between 14 and 16, okay? This is more or less, imagine that you are looking at the activities of a web server, right? Or no, sorry, of an email server, okay? You check email when you arrive to office, then we work, we do meeting, then we go to lunch, then we are back to lunch, you usually check our mail again, right? So we have a peak of activity there for the mail server, for example. But that's the same also for, I mean, I don't think you wake up at 2 a.m. to buy, I don't know, your mobile phone on Amazon, right? You sleep, I hope, right? And so that's why during the night you have lighter load, during the day you have a higher load. But they keep, so if you have an e-commerce site and you want to host your application at Amazon, then what you do, you spread your application worldwide, right? And then you build the so-called follow the sun application. So if I have an e-commerce that imagine that I work from 8 to 20, right? I start my activity now in New York, then I will grow, right, following the peak. Maybe I will shrink, then I will grow again to manage the second peak, and then I switch off the virtual machines that host my application, because in New York, people are sleeping in the night, they don't access my application anymore, right? So if you have multiple locations around the world, then what happens? Since the day starts in Asia, right? You start from Asia, you grow your infrastructure, you follow the 2 peaks, and then you switch off. While you are reaching the second peak, you have the start of activity in Europe, right? So you grow your application in Europe, then you go down, then you grow to manage the second peak. And when you grow to manage the second peak, what's going on? It's starting in US, right? So you have your overall capacity spread worldwide, really grow and shrink according to the sun, right? Because the peak follow the sun, and our human beings' activity follow the sun, let's say. And so you grow and shrink your infrastructure according to the time of the day. Right? That's really efficient, because if you spread worldwide, you are reaching your customer locally. They have good performance. They are not reaching remote site, right? If you have a single location. And today is really effective because you pay just for the resources you need, and you can grow and shrink your infrastructure, and you pay just for the use of the resources of the warehouse scale provider, warehouse scale infrastructure provider. Okay, so let's stop here. Any question? Let's see, 2 minutes. I'm not used to teach and to talk for 2 hours. I suffer. And let's continue next week otherwise. Okay, see you. Have a good day.